So, we meet again. Just like we learned to walk before we run, we had to give you just kind of a simplified situation dealing with friction before we made things a little bit more complicated. But nevertheless, that's what we're going to do. Life's complicated enough, but we're going to just make it tougher. Okay? What if, in a case involving friction, now I start applying forces at an angle? What's that going to do to our situation here? Well, we initially had our weight, and now let's say we apply a force right here. Okay? This does two things. One is that it's going to diminish our force in the x direction. If this angle right here is theta, okay, then this right here becomes my applied force times the cosine of theta. So it's going to diminish the component of my force acting in the positive x direction in this case. But it also has a subsequent effect. And that is the fact that, remember, the normal force is not simply the weight of the object. It's how hard surfaces are pressing together. So what happens is if I'm pressing down on an object, now my normal force is actually greater than the weight itself. This vector is going to be greater than this because I have to also incorporate the fact that this right here, my F applied times the sine of theta, is kind of contributing to this pressure. So my normal force in this case ends up being weight plus my applied force times the sine of theta. And so that is going to have an effect on my coefficient of friction, okay, whether it's Fk or Fs, because now remember, let's say it's mu k equals Fk over Fn, and if I'm increasing this normal force, that's going to increase the force of kinetic friction, okay? Now, let's take the contrary example. Let's get rid of all this noise up here. I'll do some erasing. Bear with me. Let's say instead that we no longer push down on an object, but rather we now pull up on this object. Okay, we have this force right here. So this is still my weight. Maybe I should use a pen. This is still my weight. This is my applied force. This is my force in the x direction, my applied force times the cosine of whatever this angle theta is. But now, when I'm lifting up on it, now the force between these two surfaces is going to be diminished. So now my normal force ends up being my weight minus my applied force times the sine of theta, because now this component of this triangle is actually diminishing this force here, okay? And so what that's going to do is it's going to diminish my normal force, which is going to make it easier for these objects to slide. So let's see how this works out in practice, okay? So I've got a demonstration problem. 100 Newton sled is pulled with a rope at a 30-degree angle with a force of 50 newtons above the horizon. The coefficient of sliding friction with the sled on the snow is 0.05. How quickly does the sled accelerate? Well, for my clip art, I happen to choose probably the least diverse piece of clip art I could. I have a white male pulling another white male, so I apologize for that. That's neither here nor there. But we have a situation here where we've got this weight right here, and I've got this force of 50 newtons right here, and I've got a coefficient of kinetic friction of 0.05, and there's going to be a force of kinetic friction that's going to be impeding my progress here. So these are my givens. I've got a 100 Newton weight, I've got a mu k of 0.05, I've got a tension of 50 newtons, and I've got theta of 30 degrees. My unknown here is my acceleration. My equation is going to be F net equals ma, so I'm going to rearrange that and say that my acceleration is my net force divided by my mass. Same thing. My mass is going to be my weight divided by acceleration due to gravity. And my normal force is going to be my weight minus this tension. I'm going to call this T instead of my applied force here. This T sine 30, okay, because I'm pulling at a 30-degree angle above the horizon here. So that is going to be my normal force. The reason I can say this is because weight is simply mass times acceleration due to gravity, by the way. Now I know that my net force is going to be my force in the x direction minus my force of friction. So let's tease this out a little bit. I know my force in the x direction is this tension times the cosine of 30. It's going to be the adjacent leg of that angle, so this would be T cosine 30 right here. And so my force of kinetic friction is mu k Fn, because we know that that is one of our new toolbox equations. So, as we kind of meander down this road of knowledge here, my acceleration then ends up being T cosine 30 minus my force of friction here divided by my mass. I'm just going to kind of rewrite what this is. My net force is what I'm trying to get here. And my net force is going to be applied force in the x direction minus my force of kinetic friction. Okay, so that's just kind of teased out there. And so this ends up being quite an algebraic train wreck. But when you get there, my acceleration becomes, this is my force in the x direction. This is my force of kinetic friction. That's my weight. That's my tension that is pulling up in the y direction over whatever this mass of this object is. Okay? And when you solve that, my acceleration is 3.8 meters per second squared. Let's say that the rope breaks, or you release the rope, and now you find you need to push the sled at a 60-degree angle downwards with a force of 50 newtons just to get it moving. What is the coefficient of static friction? Because now I've got to overcome that just to get it to start moving. So in this case, here I have this rather large-headed lad pushing, I don't know if that's a dog or a bunny. It looks like it's a bunny, it looks like. So they're pushing down with a 60-degree angle, okay, below the horizon. I've got a weight, but now my normal force is going to equal my weight plus this force times the sine of 60 degrees, because now that's what's happening. And my force in the x direction is going to equal my force that I'm applying times the cosine of 60 degrees. I can get that from this problem. So my normal force is going to help contribute to this force of static friction this time. Make sure it's a sub s, F sub s, because it's force of static friction. And that is going to be what we're looking for. What is the coefficient of static friction? So with this one, my net force is 0 because it's right until it starts moving. I haven't accelerated the object yet, so you need to identify that. The weight of the sled hasn't changed. The angle's changed a little bit. My applied force is still 50 newtons. My unknown is mu sub s, coefficient of static friction. My equation to solve for this, I know that my force of kinetic friction, I don't know why I wrote that, my force of static friction equals my applied force in the x direction. So mu k Fn, we said, was equal to F sub s. My F applied in the x direction is going to be applied force times the cosine of 60. So I need to calculate what my mu k is, and my mu k is going to be my Fk. That's what that is. I'm just rearranging this equation, okay, divided by Fn. Well, we need to figure out our normal force if we want to tackle this. Our normal force is the weight of the object plus the force I'm pushing down on it, which is going to increase how hard those surfaces press together. So that's going to increase my normal force. So my coefficient of kinetic friction, again, it should be static friction. Okay, static friction, again, apologies. My force right here that I'm applying is going to be equal to my force of static friction over my normal force. I'm substitute in mu s equals 50 newtons times the cosine of 60 over my weight plus whatever I've increased that weight by pressing down on it, which is 50 newtons times the sine of 60. So my mu k in this situation is 0.17. If you go back to our prior situation, our mu k was 0.05, and I think I misspoke yet again. This is our mu s. Our mu s is greater than our mu k, which we said was 0.05. Okay, so those are two problems, two demonstration problems. This is what I'd like you to tackle for next time. Number 9 is a little bit of a throwback. It's related to equilibrium, kind of like the cat burglar type situation. And 77 here is a little bit sneaky, but you're trying to offset gravity by using static friction. Just kind of be aware of that. So I want you to tackle that. Not a long assignment, but it should prove daunting enough that it'll take up a little bit of time, but it'll serve as a good springboard to further problems downstream. I apologize, that's 22 minutes of me talking. That's more than you want to hear on a Friday or a Monday. Nevertheless, if it's the Friday group, have a good weekend. If it's the Monday group, hope you off to a great start this week.